Okay, that will be basically a chemical reaction that's controlled by enzymes and hormones. Okay, so let's look at what's happening now then once the seed has decided to break dormancy. Okay, so when the seed breaks dormancy, what we have happening here is germination. You guys will see some seeds germinate in class right before the respiration lab. We'll get some going and some germinating. You'll get to see that. Okay, so the first set, the first thing that needs to happen with the seed is it needs to take up water. Remember, the seed's dried out. Okay, it's got this hard seed coat around the edge, so it needs to take up water, and that's called imbibition. When it takes up this water, okay, and so when the seed takes up the water with the imbibition, okay, that's going to help rupture the seed coat, because remember, the seed coat is hard, so we have to essentially break it off of the plant so that it can grow and develop. So when that seed coat breaks, that's going to start a lot of those chemical reactions, metabolic changes that allows the plant to resume growth. Remember, the plant had basically stopped growing. Metabolism was non-existent. So the environmental conditions are right. Temperature is good. There's plenty of water. So the seed begins to take up water. That breaks this seed coat, which then triggers these chemical reactions, these metabolic changes that will encourage growth. Okay, the imbibition is triggered by a low water potential of the seed. Okay, and water flows from high to low, right? So I've got a low water potential in the seed, so that encourages the seed to take water up. That's going to be the second half of this video, as we're going to talk all about water potential and what exactly that means. Okay, the last thing you need to know about the seed is what the radicle is here. Okay, so the radicle is the first part of the seedling that emerges. So it's the first part that's going to emerge from the seed, okay, and it's essentially a root. Okay, it's an embryonic root, and so it's going to grow downward. Okay, and it's going to grow downward and anchor down into the soil, where the other portion of the seed, so you can see there's the radicle that's growing down, okay, and then there's two ways that the seed can essentially come up through the soil to be able to do photosynthesis. Okay, the radicle we can form this hook, okay, and so then it can pull it upright. You see, as it's growing and growing and growing, it's pulling the plant upright. Okay, or the radicle can go just straight down. Okay, and the plant can essentially just emerge from the other side and go straight up like a grass would. Okay, so let's look at some of the ways that seeds are dispersed. Okay, so I also want you to start thinking about their evolutionary importance. Why was it evolutionary? Why would it be important for seeds to be dispersed by wind, animals, water? Okay, so we've got dispersal of the seed by wind. Okay, if you notice the shape of these seeds, okay, they are physically shaped to catch the wind, okay, so that they can easily travel on the wind. They're usually very lightweight. Okay, look at our animals. Okay, so there's basically two ways that the seeds can be spread by animals. They can either hook onto the animal, okay, like a burr that would get hooked into the animal's fur, okay, or it can essentially be contained in the fruit, and so as the animal will poop it out. Okay, it will come out in the animal's excrement as the animal digests it. Water. Okay, plants that live near water, it's very important that they have seeds that are able to float. Okay, for example, a coconut is able to float. They need to be able to survive in the water. Bursting. Okay, essentially with a bursting seed, the seed pod will tighten. You can see the wrinkles here in the pea pod here, okay, in the jewelweed pod. So the seed pod will tighten, creating tension, and it will burst and essentially spit the seeds out. And then there's also the seeds can travel by humans. Okay, so we're going to jump over now to water potential. Water potential is extremely important to how water will move throughout a plant and how water moves in general. It's not only applied to plants. Okay, so what water potential is it gives us a quantity. Okay, it allows us to essentially measure the tendency of free water to move from one area or another. Okay, so it quantifies our tendency of free water. And when we're talking about free water, I'm talking about water that is not bound to solutes. Okay, so it quantifies my tendency of free water, so not bound to solutes, to move from one area to another. Okay, and the reasons why it would move from one area to another would be things like osmosis, gravity, and pressure as well. Okay, mechanical pressure, essentially pushing down, or tension pulling. So any of those things could help encourage the water to move from one area to another. Okay, and so in doing this, water potential then is going to predict which way the water will move. Because we can get a value on each side of the membrane, and water will move from the higher value to the lower value. Okay, it is expressed. Okay, so it is expressed in potential energy per unit volume. Okay, it's represented by the Greek letter psi. Okay, so that's how you'll see water potential represented. You may recognize this from the first semester, especially with the osmosis stuff. You've seen this symbol before. Okay, so it is represented by the Greek letter psi. Its units are what are called megapascals. Okay, so it's represented by megapascals. So pure water that is open, that's in a container that's open to the atmosphere under standard conditions. Okay, and so standard conditions would be about 25 degrees Celsius, okay, and 1 atmospheric pressure. So not, not like way up in the mountains or anything like that. Okay, so pure water in a container, again, open to the atmosphere under standard conditions, is 0 megapascals. So it has a water potential of 0. Okay, just to kind of give you an idea of this, 1 megapascal is equal to about 10 times the atmospheric pressure at sea level. Okay, so about 10 times the atmospheric pressure at sea level. Okay, so that's pretty significant there. And the internal pressure in a living plant cell is about half of a megapascal due to the osmotic uptake of water. So essentially, the air pressure inside of a plant is the water pressure inside of the plant cell is about 2 times the air pressure inside of an inflated car tire. So there's a significant amount of pressure put on the cell walls of these plants. So the addition of solutes is going to lower water potential. Okay, so when I increase the solutes in my solution, okay, that's going to lower its potential. Okay, it makes it more negative. Okay, basically what it does is it takes up the quote-unquote free water. Okay, the water molecules are more attracted to the solute, and so they're less likely to move. Okay, so when I add solutes to the water, that's going to lower its potential. It's going to make it more negative. When I increase pressure, okay, so when I increase pressure to the solution, to the water, okay, that's going to increase its potential, make it more positive. So we can have negative and positive water potentials. We don't just stop at 0. Okay. Free water, like we said before, free water will move from a region of a higher water potential to a region of a lower potential if there's no barrier to it. Okay, so again, high to low based on our numbers. Okay, so what exactly do I mean by potential here? Okay, so we've been talking about water's potential. Okay, and so what that is it's essentially a representation of the potential energy of the water. Okay, the water's ability to do work when it moves. Okay, so that's all the potential energy is. Okay, it's water's capacity or ability to do work, again, when it moves from that region of higher water potential to lower. Okay. Again, the water potential for solutes is going to be negative. We mentioned that just a minute ago. So let's talk a little bit more about that. So if you remember water forms those hydrogen bonds, right, between other water molecules. Okay, and so what happens when you add solutes to the water is it interferes with these intermolecular forces here, okay, between the water molecules. And so if something is able to dissolve in water, it's because water is more attracted to the solute than the other water molecules. Let's say you have some sugar or some salt dissolving in the water. The water is more attracted to that sugar or the salt than to the other water molecules. So it disrupts these intermolecular forces here, in particular the hydrogen bonds are what we're talking about here. And so it makes the water molecules less likely to move. So it decreases their potential to do work. And so when we decrease their potential, we're going to start abbreviating that like this. When they decrease their potential to do work, okay, it makes it more negative. So when we add solutes, okay, that becomes a negative situation when it's not pure water. If I add sugar, if I add salt, whatever the molarity of my solution is, and we'll talk very briefly about molarity in just a second. Okay, but whatever the molarity of my solution is, that's going to have a negative impact on its ability to do work. Okay, so very, very briefly, for those of you that have not seen this yet, which would definitely be your sophomores here, okay, we do need to talk very briefly about molarity. First of all, Ms. Wallace wanted me to let you know that molarity is represented by a capital M. Okay, moles, lowercase m, O-L, meters, lowercase m, molarity, big fat capital M. So I'm here to really emphasize that. Okay, so basically all molarity is a measure of concentration. Okay, and it's our essentially grams per liters. Okay, it is important that you realize that it's over liters. Okay, so it's over liters. When I make all those solutions for you in the osmosis one, those are, remember it was like 0.2 molar and 0.4 molar and 0.6 and 0.8 and 1 molar. Okay, and so that was based on the amount of sugar essentially that was dissolved in per 1 liter of solution. Okay, so as it grams or moles per liter. So again, when we talk about molarity, again, it's just essentially a consistent measurement of concentration. Okay, so let's look at the equation for water potential. Remember I told you water potential is represented by the Greek letter psi. Okay, so water potential equals the solute potential plus the pressure potential. Okay, so this is my water potential. This is my solute potential. And this is my pressure potential. Okay, so water potential is my solute potential. That we said is usually going to be negative. It's going to be negative because it's going to disrupt water's ability to move. And then my pressure potential, which could be positive. Okay, so solute potential, like I said, is going to be directly proportional to molarity. It's sometimes called osmotic potential. So if you ever see a word problem or description where it says osmotic potential, that's the same thing. Okay, and like I said, it is directly related to that molarity. Okay, directly proportional to that molarity. For pure water, solute potential equals 0 for pure water. That means there are no solutes in there, so that water is ready to move. Okay, pressure potential. Okay, so your pressure potential can be positive or negative. Okay, it is relative to atmospheric pressure.